primary goal of this experiment was to calibrate a photocell. The process of calibrating the photocell required an understanding of the physics behind the photocell functions, being able to design a setup for the experiment, finding the system parameters of the sensors, and understanding the limitations of the sensor that contribute to its overall uncertainty. Most photocells are comprised of a thin strip of cadmium sulfide. Cadmium sulfide has photoresistive properties that allow its resistance between its terminals to change depending on the light intensity it is exposed to. The photoconductive effect is a phenomenon where emitted photons from a light source excite electrons in the valence band of the cadmium sulfide to the conduction band. This allows for charge carrier movement with sufficient excitation, thereby decreasing the resistance between the photocell terminals. The overall setup includes a light source powered by an Arduino Uno, the workstation with which all MATLAB and LabVIEW calculations were performed, a lux meter used as a reference instrument, the National Instruments MyDAC assistant, and the photocell circuit. After importing the data from the experiment, static and dynamic calibration was plotted. In the static data, we see that it's best to create two linear regressions. From the interpolation, the static sensitivities of the sensor were found. Since the static calibration was performed by going from dark to light, from light to dark, the static data was split into two data sets. The maximum difference between the polynomial curves was found to find the hysteresis error. The dynamic calibration was performed by quickly going from dark to light conditions. Next, a z-plot was created using the dynamic data. Looking at the linear portion of the z-plot, one can interpolate the slope of that line, which is equal to -1 over the time constant. From there, the time constant can be solved. In summary, the system parameters are as follows. To find the design stage uncertainty of the sensor, it is important to consider the propagation of errors due to the sensor apparatus and its reference instrument. The first error that was considered was the linearization errors. Again, since there are two linear regressions that were performed on the static calibration data, there will also be two linearization errors. Next, the zero drift errors were also calculated. The next error that was considered was the quantization error of the MyDAC. Since there are two static sensitivities, there will also be two quantization errors. Next, the hysteresis error was found. Next, one must consider the reference error of the lux meter. There are two different design stage uncertainties for the two different ranges that were used in this experiment. The uncertainty for the range of 0 to 38 lux was found to be 3.522 lux. The uncertainty for the range of 45 to 172 lux was found to be 3.523 lux. In summary, the following characteristics were calculated. The static sensitivity in the range of 0 to 38 lux was found to be 0.05570 volts per lux. The static sensitivity for the range of 45 to 172 lux was found to be 0.005447 volts per lux. The sensor time constant was found to be 0.172 seconds. The design stage uncertainties of the sensor were found for the following ranges. In the range of 0 to 38 lux, the overall uncertainty was found to be 3.522 lux. For the range of 45 to 172 lux, the overall design stage uncertainty was found to be 3.523 lux. Thank you for watching the process of calibrating a photocell.